Okay. So this is my pleasure to introduce Eric. So Eric is a returning PhD from the University of Southern California, US. And so now he's a research scientist at NVIDIA, working mostly on the WARF framework with his colleagues. And so today we will talk about the high performance transfer simulator in WARF. So thank you very much for being here and also sponsoring the work.
Okay. Yeah, thank you very much for organizing this and inviting me to the workshop. So it's very exciting to have the focus on differentiable simulation. And today I want to talk about NVIDIA WARF, which is and you can just click and store. And it allows you to write kernels in CUDA. And they and then it gets really fast. So you can still leverage the high-level ecosystem from Python to use deep learning frameworks like PyTorch and JAX, and then also implement a simulator in this high-level framework, but still get the speed you get from CUDA. And on top of this, we also do automatic differentiation using code generation, so that the kernels you write will be automatically differentiated, so that you can get gradients really efficiently. So we also supply a bunch of tools to do simulation, like we have acceleration structures for meshes, for volumes, and sparse structures like this OpenVDB, volume-based data structure, and also hash grids, for example. And yeah, so as I said, we integrate with PyTorch and JAX. And we also have this omniverse integration so that you can render some nice real-time ray tracing scenes that you can that you simulated with WARF. So the idea behind WARF is that we are actually not competing with PyTorch or JAX directly, because these frameworks focus on tensor operations. They are really good at writing neural networks, like big matrix multiplications and other tensor operations. And when you write a simulator, the difference is that you often have these tiny operations that only operate on like three-dimensional vectors, or they need lots of branching. So here I have an example where we want to compute the closest point to a triangle. And as you can see, there are a bunch of these if conditions. You just have these points that are three-dimensional. And you don't really want to completely redesign your algorithm just to make it fast on a GPU, like writing this in PyTorch or JAX. That requires you to use some where clauses where you need to write both sides of an if condition, and you have to think about batching all these inputs. So in WARP, the difference is, and this actually is WARP code, that you can simply write this as a normal program that you are expected to do, like in C or any other imperative language. And you just write the logic as you would in a normal framework, and WARP takes care of parallelizing it on the GPU. So every triangle could be done on a GPU thread, and then it gets parallelized massively. And you get also gradients on top of it. So even if we have these if conditions, the code generator will take care of computing gradients for this. So the difference to just writing CUDA code by hand, of course, is that we don't need you to write C++ code here. You also don't have to write your gradients by hand. So it's all taken care of by the framework that we have. And also you can still use the Python ecosystem. So PyTorch and JAX are directly supported from WARP. And you don't need to write all these wrappers around it. So we make it really easy to write a torch autograd function around your WARP kernels. We have a bunch of examples for this. And so it's easy to get started with this. Just to give a brief overview of how the compilation pipeline looks like. So when you write WARP code in Python, we analyze the AST, the abstract syntax tree. Then we generate C++ or CUDA code. And this gets then compiled using NVRTC. So it doesn't even need the CUDA toolkit to be installed. It's just using the CUDA drive as a NVIDIA driver to generate PTX or Kuben, and then you can launch this. So it gets compiled and runs on modern GPUs really fast. And we also take care of caching. So it's really fast to have small modules that can be reused. So you don't need to wait a minute all the time for the JIT compiler to finish, because many things are cached. So it's typically faster than JAX in this regard. So there are many use cases for WAP. For example, in data processing, we have some really fast mesh query functions. We can also do image processing really fast, like shader-based coding, essentially. Then, of course, simulation is a big use case for us. We have rich support for rigid body dynamics, soft bodies, and MPM, and other kinds of simulations. We can integrate with PyTorch, as I mentioned, to do machine learning and also scientific computing. And yeah, in particular, these inverse problems where you need gradients to optimize parameters. So that's what it's made for. And also, if you write something like advanced environment for reinforcement learning, where you need maybe special handling of the observations, or you need the custom reward function, that's also where WAP could be really useful, because it's really fast and it gives you these spatial math functions to handle quaternions and transforms, which is not really that easy maybe in PyTorch, for example. So the SDK consists of those three main modules. We have the core module that handles the math library. It has the spatial computing functions, and of course, this full mechanism of generating code out of these WAP kernels. Then we have WAP Sim that has a bunch of integrators. So we have Featherstone for articulated rigid body dynamics. Then we have XPVD, or extended position-based dynamics. That's more like graphics approach, but it's really stable and gives you hard context. And then we have a Spring-based Euler integrator, where everything is represented by Spring, so all the joint constraints and so on. We have importers for URDF, MJCF, and USD physics. And we also support soft body dynamics. And there are a bunch of open source implementations for MPM also now. So you can do continuum dynamics and other things in WAP as well. And then we have also direct support for FEM. We have WAP FEM is like some high-level way of defining the problem, and then it gets solved on some domains. So you can solve heat equations, but also soft body problems, and MPM with particle and cell methods implemented directly in WAP FEM. So to get more into the details of WAP Sim, so this is our provided module for simulation. We have different integrators, and here on the right you can see a simple example how this looks like. So we have a model builder that is similar to Mujoko, where you need to define the model that defines like the articulation or the topology of the system, and then you can also define parameters. And then we have this parse URDF function here that loads like a carpool or some other model, and then you finalize. That will create this final model out of a model builder that actually allocates the buffers in CUDA. And then in this case, we use the Euler integrator, which uses springs for the joints. And then we allocate the states, and then we can just integrate over time the simulation and get the states out of the system. And so everything you can see here can be differentiated through. So when you record the states on a tape, then it's possible to get gradients from it when you define a loss function over states, for example. So the state contains like the joint coordinates and generalized coordinates, but also the rigid body state. That's similar to Mojoko's data model, essentially. Then the control input is the joint forces and also the maximal coordinate forces, if you want. And then the model defines the static information that typically doesn't change throughout the simulation, like the parameters or the topology of the articulation. Then we have our integrator that has a simulate function, and then you get the next state out of it. It will be computed. And so this whole process inside simulate is differentiable, including the contact handling. So we can use automatic differentiation for this. And in warp, this is really explicit. When you want to compute gradients, you need to allocate this warp tape, and this will allow you to record these operations. So when you call kernels, like using warp launch, then these launches will get captured on the tape. You can compute the inputs to those kernels that we just launched. And the whole computation is stored inside a graph. And that is really the thing that speeds up everything tremendously. And we've done this for reinforcement learning as well, where the reward computation, the simulation, everything is on a single CUDA graph. And you just need to make this one Python call. And we have basically no downsides anymore from Python in that sense. So here's a simple example where the goal is to tune the initial velocity of this particle so that it reaches the black box. And over time, as you can see, we get closer and closer. This actually uses LBFGS from PyTorch. And we just wrap our simulation for this particle bouncing off the wall inside the torch autograd function. And so the gradients come from warp, and then it finds a really fast solution. Another example that we did is using this for drone simulation. So I looked at the AirSim model that they have for simulating how the currents inside the motors yield certain thrusts on the drone. And then we also have a model for air drag here that's based on angle of attack. And that's all written in warp. We use warp sim just for the rigid body integration here. And then we optimize the trajectory of the drone. And since it's so fast, we can do MPC. So we run the full simulation online real time, and then can solve to reach certain waypoints really easily, and also account for obstacles, just adding this to the cost function. And we can do this also in parallel, similar to the sampling-based MPC, where you can make sure you find really good solutions by parallel rollouts, and you still get gradients for those. So you can combine sampling and gradient-based MPC. Another example is this FEM simulation of a bear. So we have this bear that consists of 2,000 tetrahedra, and then surprisingly, just with gradient descent, it's able to find this motion where we actuate certain elements in this tetrahedron with some neural network. And then these activations fire in a certain pattern so that it actually learns to run in this way. So this is really surprising to me that this works so well, because typically in rigid body simulations, we don't see this just emerge by itself. But it seems like FEM might be easier for this. Another example is this soft shell simulation that also handles fluids, where we can optimize the swimming behavior of this jellyfish. And that also, I think, uses PyTorch to just use the optimizer from it. And we use the gradients from warp here. And this also gets rendered in Omniverse, which we have direct support for. So just export the USD file for simulation, and then you can render this in real-time ray tracing mode. And finally, another example where we optimize the initial velocity of this cloth so that it reaches a certain goal point at a certain point in time. And here also, you can differentiate through the cloth simulation, this highly nonlinear system where we also have air drag simulated. And it's a really complex simulation where it's able to optimize even through those computations. So just to give a brief overview of some acceleration structures we provide inside warp. So first we have the mesh structure that allows you to do really fast queries, like finding the nearest point of querying whether a point is inside a mesh and getting the nearest triangle, also do ray queries and bounding box queries. And then we can also fit the acceleration structure really fast. So internally, this uses the bounding volume hierarchy to speed up the queries. And here in this example, we have actually an animated mesh of this dancing figure. And there also at every frame, we need to refit the mesh. And that happens on the GPU. And then we can run the FEM class simulator and do the queries for all the particles in the class against the mesh. And that happens so fast that it runs in real time, even for these 32,000 triangles in the class. Another structure we have is the hash grid, and that's for nearest neighbor queries. So we can do really fast queries for particle simulations, like the contact handling. So here's a simple simulation for the discrete element method, which we have shipped with Warp also. So it's just 200 lines of code and uses a hash grid. And that again can be rebuilt on the GPU and yeah, runs really fast. So nothing has to leave the GPU for these simulations. And then we also have OpenVDB support. That's really good structure for SDFs. So we can store highly complex shapes in this SDF structure. And that also gets accelerated on the GPU. So when you develop these differentiable simulators, it's often challenging to find bugs or just to see whether gradients are correct. So we supply some tools for that, like a simple way of plotting Jacobians, then also to do grad checks similar to PyTorch, but here it's written for Warp. And so we can look at the inputs and outputs of the kernel and see that the gradients actually match finite differences. So that's like the lowest level. And then if you have a complex computation with many kernels, then it's really helpful to have some way of visualizing it. And that's what this warp.tape visualize function does, where you get the like the graphless visualization of how the arrays feed into kernels. And here you can actually see when there's this green array, then it means that it has gradients enabled. And if there's a gray array, then this doesn't have gradients enabled. And that's a good way to sometimes see where gradients stop flowing. So if you forgot to set requires grad to true somewhere, or if maybe the wiring isn't correct between the kernels and the arrays, then you see that immediately in these kinds of visualizations. Yeah, so there's also many open source or other research projects that used Warp. For example, from MIT, there was this project on learning a constitutive model for the material point method. And they actually were able to fit the model so well that it could match real data. So they have this door shape here that they draw. As you can see, the key points, they almost overlap here with the simulation. And they also were able to generalize. So they train the material model on some small scale simulations, but they are able to scale up to 30 times larger environments and even unseen geometries. So the way this worked is they had this NPM simulator written in Warp here in the middle. And that's also a PyTorch function again that computes gradients for all these particles. So these are really thousands of dimensions that they need to differentiate through. So no way to use finite differencing for this. And then they use the neural network for the elastic law and the plastic law. And those together are able to fit to real data eventually. So from these particle-based simulations, you can get some really realistic behaviors. Another project that also used NPM is from UCLA, CMU, MIT, and University of Toronto, where they learned the stress fields. And here they also were able to reach really close, close simulations to real-world behaviors. Then we also had a project with Autodesk now on a big differentiable Boltzmann fluid dynamic solver. So they have this XLB project that simulates wind tunnels and many applications also for drone design or designing some mechanisms under a certain fluid dynamics constraints. And so they used warp and saw a big speed up over JAX and PyTorch, because in warp we actually control how kernels are run, so you get this low-level control and also the allocations. It's not implicit. You really have to create a warp array to make something happen. So it's easy to keep track of how memory is allocated in warp. Yeah, so here's an example for the spin tunnel. Then here's another interesting use case where warp is even faster than handwritten CUDA code, because we have just-in-time compilation. There's sometimes information you have at the time when you generate code. So that's not available when you write it in C++ necessarily. And here in this project, that's for simulating protein docking for drug discovery. They were able to use warp to specialize certain kernels at runtime, and then they get a really huge speed up, like 10 times over Torch, and even a good speed up over native CUDA code. Here's a project we did with University of Toronto on generating grasps. So we have a differentiable contact model here, and the goal is to optimize the configuration of a robotic hand so that it reaches a stable contact around a large variety of objects. And we leverage this differentiable mesh query functions we supply in warp to have a fast and large-scale simulation. So we are able to generate over 1 million grasps in just 140 hours on a GPU. So that is also another project from CMU in this case is this reconstruction project. And they used the videos from like animals doing certain things. And then they have a deep learning model that for every frame predicts how the mesh is deformed. So they have a mesh of the dog in this case doing certain behaviors, and it should play. And then they get these frames that are a bit jittery, so they're not really realistic. And then they use warp to use these reconstructed motions of the articulation to make it physically plausible, so that there are no interpenetrations with the ground and that the joint constraints are also maintained. So that's a nice example where a differentiable simulator is inside this deep learning based network, and where also you need these gradients to infer these behaviors. And yeah. And then also what I mentioned earlier, that sometimes even if you don't really care about differentiable simulation and you just want to do some custom things on top of an existing physics engine, it could be useful. Like in this case, we had the animal robot training in a reinforcement learning environment in ISAC-Sim. And the goal here is to compute the observation for this robot. So we simulate a LiDAR scanner and then use these mesh queries we have in warp, like really fast ray casting, and then use this as an input to this neural network that can now learn from these point cloud inputs. So this actually runs on a real Jetson hardware. So it's used and deployed already with warp in the loop. And then we had this project on differentiable reinforcement learning, where we tackled the problem of actually optimizing trajectory policies in a differentiable simulator. We found that when you just do a simple gradient computations with these large or these long rollouts using backpropagations through time, that these gradients are often really noisy. So the typical reinforcement learning algorithms don't really converge at all. And what we did is to shorten the horizon over which the reward is computed, and then stop the gradient flow between these horizon windows. So this is the idea behind this short horizon actor critic work that also got picked up in other works now. So here's an example for 152-dimensional humanoid, where these muscles need to be actuated. And I think this is also a good example of where finite differencing would probably be not sufficient to do this fast enough. They actually want this parallel simulation of the gradients, and you cannot really shortcut it so well. I mean, it's possible, it's just slower. And then here's an example where we extended this work and actually tuned the lengths of these horizon windows. In the previous work, we just picked some lengths that worked really well, But in this work, we actually saw that often these running cycles, these gates, typically had the same length as the horizon window that was chosen before. So instead, here we try to discover it automatically and basically stop the gradient flow at these contact events for locomotion. And that really helps a lot with the convergence. And we also get much higher quality policies in the end. So they are faster and they also look more natural in many ways. Yeah, so one last point I want to make is on the roadmap that we have. So right now, Warp Sim is its own project. You just can pip install it, but we also want to do this more in a structured way for reinforcement learning. So we are looking right now to use it as a backend for Isaac Lab. There are not all the features there yet that we have in Isaac Sim or in PhysX, but our goal is to make it really this platform that it could be built on in the future, and also to eventually have differentiable simulation environments there. So to summarize, Warp is the open source library, and I encourage everyone to try it out. And it runs on all the platforms. As long as you have an NVIDIA GPU, you can use it. And yeah, so that's it. Thank you very much.
Do we have questions? Yes.
That's a good question. So I simulated a lot of the duration is like freezing like from content rigid body and from object. And then personal experience like super stable that it's like a work going to like a full disable integrated future release to get actually like somewhat more stable content handling in the future.
Yeah, possibly. It's not right now our main focus, I would say. But yeah, I think, yeah, maybe, I mean, yeah, I don't know if we will do it, but there may be other groups that also can implement this. So, yeah.
Yes, you showed that those if-else statements. I wonder what do you do with them to kind of make them differentiable?
Yeah, so we just have the input that gets replayed in the backward path, and then you know which branch you were on, and that's the gradient that gets propagated. So it's just the same propagation. There's no magic thing to soften these if conditions.
Eric, you mentioned you in optimization you use the warp for function you are optimizing, then you pass that to PyTorch to run autograd and use Adam or something. Why not implementing Adam and all the optimizers in warp and provide it?
Yeah, we have this also implemented in warp. But I mean, here I wanted to show that we are playing nice also with PyTorch and that you have your existing optimizers. So it's not like you need to rewrite everything.
So what's the performance comparison and the advantage of the
Yeah, with Tai Chi, we've done some experiments also. I think it was faster. We have some class simulation. Not sure. Yeah, I have some slides also, I think, on this. Yeah, we've done the comparison. There's something on the website also in the documentation we have. Yeah.
So from the usage perspective, I actually just
Yeah, I think what we do is we support it now. So I'm not sure about Tai Chi if that's still happening. But also we look into other approaches, like we have the CUDA acceleration, now have tensor core support. So there's more things inside CUDA that we do also to speed up computation. Also, NVMAS is now a new library that exposes QSolve, QBlast, and this will also be part of Warp then, so you can get easy access to these really advanced functions.
the last question maybe.
Yeah, so you can write a Warp kernel and put this inside JAX and even use JIT compilation through it. I think we don't support gradients for that though yet. But for PyTorch, it's completely compatible. You can use torch tensors, map them to warp arrays without copying, and then also the gradients can be propagated easily there.
Okay, we can thank you again, Eric, for the minutes.